from its mean position is. So we are looking for the time. Okay. So knowing the displacement of a body executing simple harmonic motion as y is equal to a sine omega t, or x is equal to a cos omega t. And over here, the question hasn't been specific on the oscillation, whether the oscillation is along the vertical or along the horizontal. But usually we take it, the oscillation is taken to be along the vertical. Meanwhile, if you chooses to look at it along the horizontal, once the question never specified it, you are not wrong. So if y is equal to a sine omega t, then if displacement is a on root of 2, which is equal to an amplitude of a sine omega t. Don't forget, omega t is equal to theta. So if I want the phase angle, I quickly change this to theta, because in fact the phase angle is theta, and this describes the position of the body with respect to the mean points. So the first angle describes the position of the body, the oscillating body or particle, with respect to the mean point. Okay. So that's the phase angle. Therefore, we are to find the phase angle. The question asks that we find the phase angle. Let me go back to the question to see. Okay. So, here we are to find the shortest time it takes to reach this displacement of a on 2, or a on root of 2. So sine theta is equal to a on root of 2 times 1 over a. Of course, we have to divide through by a. And when you divide through by a, okay, the division changes to be multiplication, and the denominator fraction reciprocates. So we have this. Therefore, we have sine theta equal to 1 over root of 2. Theta therefore is equal to the sine inverse of 1 on root of 2. And please, what's the sine inverse of root of 2? What's the sine inverse of root 2? Hello, what's the sine inverse of root 2?
45 degrees.
So this is 45 degrees. Now we also know theta to be equal to omega t. So we are looking for the shortest possible time, t. Therefore, we equate omega t to 45 degrees, and because omega is equal to 2 pi over the period capital T, we express the phase angle, which is 45, in radians. And 45 degrees expressed in radians is equal to what? Priscilla, what is 45 degrees in radians? Where's La Ama? Okay, Ama, let's go. Ama, what is 45 degrees in radians?
Sir, please, I got 0.785 rad.
Oh, give it to me in multiples of pi. 45 degrees in pi. Yaba, what is it? Hey.
Please, I got 0.25 rad. Pi. 0.25 pi rad.
Do not express it in decimals. Give it to me in multiples of pi. 45 degrees in radian. We've done circular motion. Please. Yaba, Equia, and Co. What is 45 degrees in radian?
Pi on 4.
Oh,
Yes.
let's not waste time in responses, please.
On 4.
I get so disturbed when you do that. Pi on 4. So this is pi on 4. Okay. So we were given this. We were told from the question that the period is capital T. Therefore, make T the subject. Pi will cancel out. Okay. Then we'll have T equal to period times 1 on 4. Okay. 2T is this. Okay. Therefore, T would be equal to the period capital T divided by 8. So this will be the shortest distance, which will give you a displacement of this value. That will be the shortest distance that will produce a displacement of y is equal to root a on root 2. No, it isn't. Anyway, a lot of you got this correct. It isn't a difficult question. Then question 2. The amplitude and the period of a body executing SHM are 5 centimeters and 6 seconds, respectively. So the amplitude and the period, we are told, are 5 centimeters and 6 seconds. A is equal to 5 centimeters, period equals 6 seconds. At a distance of 2.5 centimeters, so at a displacement of 2.5 centimeters, away from the mean point, the phase will be, so we are looking for the phase angle. S, and I said, what is the phase angle? When a body is describing circular motion, it is also describing simple harmonic motion. So assuming it starts from this point A, then move to a point B. This will correspond to a certain angle at the center, the angular displacement theta. Okay. And so would give you a displacement at this point if we are looking at vertical displacement. So the phase angle theta describes the position of the body with respect to the mean point. So if we are considering this to be the mean point, the center, then The angle will describe the position of the body with respect to the mean point or the center O. That is basically what it means. So if you are asked to find the phase angle, it means find this angular displacement theta or omega t. That's all. So at a displacement of 2.5, if you are taking the oscillation to be vertical, then y is equal to a sine theta. Okay. Therefore, if you are also expressing it as omega t, then you must understand that omega t is equal to theta. Therefore, 2.5 is equal to an amplitude of 5. When you divide through by 5, we have sine omega t to be equal to half. When you take the sine inverse of both of the right hand side, you have this equal to 30 degrees. It means that the phase is an angle of 30 degrees or pi on 6 radian. That's the phase. That's the phase. Now, let me also take the opportunity. Okay, before we continue, please, if you have any question concerning this one and this one, please quickly ask for clarification. Any question on what you've done so far? Okay. All right. Let me drop attendance. Okay. Very, very important. Let me drop attendance. Okay, so let's continue. Now, during my I realized that some of you, please, I'm not disputing the fact that you can also express your displacement equation, okay, along the horizontal, where there will be the need of you to use cosine. That is equally right. But it is just that we often look at the oscillation along the vertical, the reason for which we are fond of using sine and not cosine. But every harmonic function actually can be expressed as a sine or cosine. I saw a very blatant mistake committed by some of you. Y is equal to a sine omega t, and this omega can also be a sine 2 pi f t, because omega is equal to 2 pi f. It can equally be 2 pi over t times this. In the question 2, in determining t, I saw that some of you divided through by a. This is correct, because a multiplies sine omega t. But please, sine omega t is not what we have here, isn't sine times omega times t. No. This is trigonometry. Omega t is equal to angle, phase angle, phi, theta. So this sine is not multiplying omega t. It's an angle. Okay, it's an angle. So you cannot divide through by. Then in determining t, I saw that y over a is equal to sine omega t. Then I saw a division of omega. Please, it's not like that. Sine isn't multiplying this. It is trigonometry. This is an angle. So please, let's take note. You can't divide through by omega to eliminate. No. So after doing that, the next thing I saw was that, okay, so if sine t is equal to whatever has been obtained here, maybe 1 on root of 2, then t is equal to sine inverse of 1 on root 2. No. Omega t is an angle. It's trigonometry, not algebra, where there is simple multiplication and all that. Class, is that understood?
Yes, sir.
Yes, sir.
Very, very important. Okay. The displacement equation of a body executing simple harmonic motion can be written in different forms. One of the forms is y is equal to a sine omega t, or x is equal to a cos omega t. When the equation is like this, what it means is that this is a wave. When you come to wave motion, you understand this better. This is a wave, meaning that the harmonic wave starts from the mean point or the origin. Okay, start from the mean point or the origin. So if you draw a sine function and it's like this, meaning this wave is starting from the mean point. If it's a cosine function always start from the amplitude, the maximum displacement. So cosine functions like this. So if you see a wave starting from the amplitude, it means this is a cosine function. For sine functions, if phase angle or the phase difference is 0, it always starts from the mean point. Okay, for sine function, this is it. Now, the same wave, the displacement equation can also be written as this. You can also see y is equal to a sine omega t plus or minus phi. Okay, don't forget omega t is equal to theta. This is what we are calling as phase angle. Phi is what we call as the phase difference. Phase difference. For phase difference, you understand better when we start wave motion, because I will explain that into details. But whenever you see plus or minus phi, let me break it down. If you see displacement equation and you see a phase difference phi, this is also an angle. What it means is that the harmonic wave is moving away from the mean point, away from the mean point. Basically, all that is being said is that the wave doesn't start from the origin where we are starting exactly from the center. Zero. No. When it is minus, the wave is moving away from the mean point or moving from left to right. Moving from left to right. I'll explain further under wave motion. Then if the equation is written as A sine omega t plus phi, phase difference phi, all that it means is that the harmonic wave or the wave is moving towards the mean point, towards the mean point, or moving from right to left. Moving from right to left. So let me sketch something to represent all the three. When the phase difference phi is 0, I've already done that. This will start from here. Then when there is a minus, so 1, 2, when there is a minus, the wave is moving from right to left. So left to right, sorry, when there's a minus. So it doesn't exactly start from the mean point O. When it starts from the mean point, phi is 0, meaning this is it. But where there is a phase difference, phi, then either the wave is moving from left to right, and that is from left to right, there should be a minus. Then from right to left, it can be drawn as this, but the wave, okay, let me draw a third one. Right to left, it shouldn't start from 0, but the direction of the wave is in this direction, moving from right to left. Right to left. So here it is clear that the wave is moving away from the mean point by the direction. Here it is also clear that the wave is moving towards, there's the mean point, O. So it is moving towards the mean point, O. Okay. So when you see plus or minus of phase difference phi, that is what it means. That is basically what it means. Please, if you have any question, quickly ask. So, all that I want you to understand is that apart from either y is equal to a sine omega t or x is equal to a cos omega t, I can also be giving you this displacement wave equations. And that is basically what it means. Aman.
Mr. Jia, please, about the first and second formulas. Please see the first question.
Ama, your line is breaking. Ama, your line is breaking. No. Ama, come again. Ama, send me a message. Send me a message. Your line is breaking. All right, so that is it. Now let's continue with where we got to. Amma, send me a message. Send me a message. Your line
Please,
is
can you
breaking.
hear me now? Can you hear me now?
Okay. I can hear you now, Amma. All right, so let's continue our discussion on velocity. Velocity. So last time we derived the velocity equation because we see the body moving up and down around the mean point O. There is a regular change of the displacement of the body with respect to the mean point or with respect to time. So this is center O. This is the amplitude A, and then downward amplitude minus A. So we see this body moving up and down, okay, around the fixed point O. This is the extreme. So extreme, the first extreme, the second extreme. So because its position is changing with time, it would yield the velocity function of a body executing simple harmonic motion. Why? Because its displacement is changing with time. And so we had to get the velocity equation, we need to differentiate the displacement function with respect to time. And this gave us A omega cos omega t. And that is the displacement equation in terms of time. So this is the displacement equation of a body executing simple harmonic motion in terms of time t. Meaning that we can use this to determine the velocity of a body executing simple harmonic motion at any given time t. Okay. And last time, I think we demonstrated it, that when the body moves from the mean point and then gets to one extreme, what is the velocity? Yes, so what is the velocity of the body at the extremes? At the extremes.
Sir, please, 0.
We got 0. Okay.
Yes.
And we demonstrated this by the time taken to move from the mean point to one extreme or to this first extreme. T is equal to quarter of the period. So if the time taken to move from here to one extreme, the first extreme is this, then we can determine the velocity to be equal to A omega cos omega times T on 4. If T on 4, because we've known omega to be equal to 2 pi on period. We have T and T canceling out. We have 2 going into this 2. So we have A omega cos pi on 2. Now what is pi on 2 in degree? Pi on 2 in degree.
180 degrees.
Pardon?
180 degrees. 90.
It's 90. Pi is 180. So this is in degree, pi on 2 is 90. And because cos 90 is 0, velocity is equal to 0. So we've just proved that at one extreme, the velocity there is 0. Now, what about the other extreme? What time will it take the body to move from one extreme or to move to the other extreme? So 1, 2, 3. What will be the time? What will be the time taken to?
3 on 4, 5.
So 3 on 4 of the period, 3/4 of the period. So if T is equal to this, then V is equal to A omega cos of 2 pi on T times a time of 3 on 4 T. So T and T cancels out. 2 goes here, 2. So we have A omega cos 3 pi on 2. Change 3 pi on 2 to degree. 3 pi on 2 to degree. Or what is 2 pi?
270.
What?
270 degrees.
Good. So cos of 270. What is cos 270 degree? That is 0. So it also proves that when the velocity of the body at the extremes is 0. So minimum velocity of an oscillating body occurs at the extreme. So minimum velocity of the oscillating body occurs at the extremes. So for an oscillating body, the velocity is minimum at the extremes. Where does it have maximum velocity? Let's see. So let's go back to the diagram. It takes quarter of the period to move from the mean point to here. And so by the time it crosses the mean point, it will take a time of what? What time will it take to cross the mean point when it is returning from the extreme, from one extreme? Yes. What time will it take to cross the mean point from the extreme? Hello, talk to me.
Half team.
Pardon?
Half team.
So look at it. So quarter of the period, half of the period, 3/4, and we take another T. So the time taken to cross the mean point are half of the period and capital T. So let's use the velocity equation to determine the velocity whenever it is crossing the mean point. So using V is equal to A omega cos omega T. We have this 2 pi on T times T on 2 first. So we have A omega cos pi, and pi is 180. Cos 180 is equal to -1. Therefore, we have minus A omega as the velocity whenever it is moving from the one positive extreme to the mean point. Then when it comes to the other extreme and it is going back, the time taken is T. Let's look at the velocity.
Please, can you repeat your other statement?
Herbert, what I'm saying is that we are looking at the body. Yes, it is an oscillating body. So it is moving from the mean point to the first extreme. So it takes a time of half of the period to move from here to the other to the first extreme. Okay, then it would take quarter T, half T to come to the mean point or to cross the mean point, then 3/4 of T to come to the extreme. And when it is crossing the mean point once again, it will take a time of capital T, full period, okay, to also move from here and then cross it again. So we want to get an expression for the velocity whenever it is moving from the second extreme and crossing the mean point again. Herbert, are you okay? So V equal to A omega cos of 2 pi on T times T again. Because this time the time is this. This and this will cancel out. Then we have cos of 2 pi. What is 2 pi in degree? What is 2 pi in degree?
360.
Good. So we have cos of 360 degrees. And cos 360 is equal to 1. Okay. Therefore, we have the velocity being equal to A omega. So what we can deduce from this is that whenever the body is crossing the mean point, it crosses it with maximum velocity. The body crosses the mean point with maximum velocity, or maximum velocity of an oscillating body occurs at the what? Here, somebody to complete a statement for me. Occurs at the oh, somebody to complete this statement for me. Maximum velocity of an oscillating body occurs at the
Mean point.
At the mean point. And minimum velocity occurs at the extremes. Any question? Any question? All right. The second, Amma, I hope your line will be good.
Sir, please, can you hear me now?
Yes.
So please, I wanted to ask a question about the first formulas we discussed, the y is equal to a sine omega t or cos omega t. So please, you said the the sine function, it starts from the mean points and moves away from it, and the cosine, it starts from the amplitude and moves away from it.
No,
So,
no,
sir, how can we use
no.
this?
Hold on. What I said is this. The explanation I gave can be sine or cosine. Amma, what I'm saying is this. If you have sine omega t plus phi or cos omega t plus phi, all that it means is that this wave is moving from right to left. So the direction of the wave is this, right to left, whether sine or cosine. Or, so moving from right to left, or the wave is moving towards the mean point. And if you see sine, omega t minus phi or cos omega t minus phi, then this is the direction of the wave from left to right, or the wave is moving away from the mean point. That's what I said.
Sir, please, I'm talking of the first formula we spoke of, the one without the phase angle.
If there is no phase difference, no, Amma, if there is no phi, then the wave is starting from the origin for sine.
And for cosine, it is?
For cosine, okay, cosine is like that. What you have to understand, because for you to understand this thing so well, we must treat wave for you to see how we get this plus or minus 10. But we are applying in SHM. The reason for which I'm not going into detail as to how we came by this. But all that I want you to understand is that if this is it, then the wave is starting from the mean point for sine functions. Then if it's a cosine function always start from the amplitude. So for cosine, this is what you must expect. So get this for now. If it doesn't start from here and it's starting from the amplitude, then it's a cosine function called omega t. That's what I'm saying.
Sir. Since sine start from the mean and cos start from the amplitude, so how can we use these two formulas to solve the same question?
Which one? This one?
Like, sir, are we saying the first question we solved?
Yes.
You said we could either use y is equal to a sine omega t or y is equal to a cos omega t. But sine is start from the mean point and cos start from the amplitude. That's why I'm asking.
You will not get the same.
Use them to answer the same
you
question?
you will not get the same results. If you use sine or cosine, you are not to get the same results. Okay, but the difference in the results has to do with the fact that if this is the oscillating body, okay, when it is here, when we are at this point, it means that y is 0. Y is 0, but x is maximum. X value is maximum. Okay, now when the body gets to this point, when the oscillation, and this is where we are talking about looking at the oscillation horizontally, cosine omega t. if you are looking at it vertically, okay, at this point, at the same point, which is equal to this, y is 0. Y is 0. Is that okay? Y is 0.
Yes, please.
Hold on. X rather is 0. X is 0. Y is 0 at this point. Now, when the body is seen to be oscillating vertically, X is 0, but Y is equal to maximum. This is when we are looking at sine. So you may not get the same results, but it fits depending on where you are looking at the oscillation. Are you okay?
Yes, please.
All right. Let's quickly, I want us to quickly finish this aspect of it and then move on. So we've just realized that the velocity in terms of time, V is equal to A cos omega t. How do we apply this? At any time t, you can use this to find the velocity. Hence, this is the velocity equation of a body executing SHM in terms of time. Please take note. In some other situations, you will not be given the time. In some other situations, you will not be given the time, but you'll be given the displacement. Please be very attentive here. In some other situation, you will not be given the time, but you'll be given the displacement. And I'm going to use the diagram to explain it a little bit, then we continue. This is a body executing SHM along the vertical. Okay. Now, when you are told that at a displacement y equal to maybe 5 centimeters, what is the velocity? Okay. What are you given? This time around, you are given displacement to find V. Before, we were given time, which we express as quarter of this, half of the blah, blah, blah to find V. Meaning, you can use the same relation, connecting velocity to time to find for V when you are given displacement. Class, are you with me?
Yes, sir.
So you need to have a relation connecting velocity to displacement. All right. You need to have a formula connecting velocity to displacement. To find velocity whenever you are given displacement. As for velocity with time, we have it. Priscilla.
Mr. Adrian, please, I'm having some network issue. Can you repeat what you just said?
Okay. So, this is what I mean. We have seen that, and Amma, we are almost looking at vertical oscillations. Okay. Even though we can look at horizontal oscillation. So, V is equal to A omega cos omega t is the velocity in terms of time when we are looking at vertical oscillation. Meaning we can derive one for horizontal oscillation. And I expect you to go through it and then report to me. This is V in terms of time. So at a time of maybe 2 milliseconds, calculate the velocity. You use this because you've been given the time. Angular velocity will be given, amplitude, blah, blah, blah. Now, when you are given at a displacement of maybe y is equal to, example, 3 centimeter, calculate the displacement. Sorry, the velocity. Here, we are deficient. The deficiency is that what we have at the moment connects velocity to time. We don't have a relation connecting velocity to displacement yet. So to be able to do this, we need to have that connection. Priscilla, that's what I'm saying.
Okay, sir.
So how do we do that? Okay, we will use the same thing. We'll just play around the equation to get a relation or formula for velocity and time. This is how I want us to play around this. I want, if we substitute omega out and put amplitude squared times the cos squared of omega t, have we changed anything? Please, this cos squared omega t is the same as cos omega t all squared though. But to look professional, the reason for which we write it as cos squared omega t. If I have this, and I write it as this, class, have I changed anything? Just look through. If something has changed, tell me. Ama, Akwiadoma, have I changed anything?
No, please.
Good. Let me look for names and mention. You can't hide in your rooms and be watching me. Aha, okay. Inshira, Abba, you are all here. Kim, Lynn. So I haven't changed anything because when I take the square root of this alone, I get back my A. When I take the square root of cos squared omega t, I get back my omega cos omega t. So I haven't actually changed anything, but I'm just playing around this equation for a reason, which you understand later. So after making this modification, in trig, one of the trig identities, the sine squared of any angle, omega t, plus the cosine squared of that same angle, the sum of it is equal to 1. Please, I'm sure you know this. Hello? Are you familiar with this?
Yes, please.
No, please.
No, please.
Yay! There's a Hackman owes me. Okay, let's go through a little bit. Let's prove something. It will help you. You have a right angle triangle. Of an angle of inclination theta. The opposite is A. Adjacent is B. Hypotenuse C. Let's take the sine of theta. Helen, what is the sine of theta? From my right angle triangle.
Please, it's A over B.
A over B. Thank you. So A over B. Then help me square this. Sine squared theta will be equal to Len, have I done your work for you? Yes. Abba, help me determine cos theta. Abba,
Sir, please. B over C.
B over C. Abba, you help me square this. And I've done your work for you, right?
Yes, please.
I want us to sum this up. Sine squared theta plus cos squared theta. And this will be equal to the sign.
Sir, please. The
Hey.
sign is supposed to be
A over C.
opposite
Thank you.
over hypotenuse.
It's noted. Thank you. Okay. So we have good. So sine squared plus cos squared, we have A squared over C squared plus B squared over C squared. When we take the LCM, we have C squared. So we have A squared plus B squared. And from Pythagoras theorem, what we have here, if we square C squared must be equal to A squared plus B squared, isn't it?
Yes, please.
Yes, please.
Meaning that what we have here at the numerator is equal to what? Is equal to,
C squared.
so we have C squared over C squared, and this is equal to 1. So for any angle, when you take the square of the sine, and then the sum of the square of the sine and then the cosine, the results must be equal to 1. And that is what we are using here. So if I have sine squared omega t plus cos squared omega t, then because I have cos squared omega t here, I want to make cos squared omega t the subject in this one. Okay. I want to make cos squared omega t as the subject, and I'll have cos squared omega t being equal to 1 minus sine squared omega t. Please, is that seen? Is that understood?
Yes, please.
Yes, please.
Good. So I'm going to substitute 1 minus sine squared omega t in place of this here. So I have 1 minus sine squared omega t. And when I finish, I'm going to multiply through by the a squared, which is outside the brackets. So I have v is equal to omega out a squared times 1 minus a squared sine squared omega t. And the good news is that I can rewrite this as just clear this and then put them under within a bracket and square it. Please, are you okay up to this stage?
Yes, please.
Yes,
Sir.
please.
Okay. Now, what is a sine omega t? What is a
Why?
sine? Why? Thank you.
Why?
So, because I've managed to get y, all that I do is that, okay, then since a sine omega t is y, then I substitute y. What have I achieved? For a body executing SHM, omega is constant. Amplitude, A, you decide it. You decide the amplitude of oscillation. Maybe I want an amplitude of 5 centimeters, 2 centimeters. So you make that decision. Y can vary. At the midpoint, Y is 0. When we are moving on, Y will be increasing. At the extreme, Y is maximum. So we only see Y changing as the body oscillates. And so this gives us the relationship between velocity V and displacement of a body in simple harmonic motion. When you are given displacement of so and so, you can find the velocity V. And let's quickly apply this in solving a problem. I want us to apply this. So I'm going to give you a question so you can try. Please, if you have any question, ask, quickly ask. Yes, Abba.
Sir, please, did you say we can choose the amplitude ourselves?
If you see, for an oscillating body, the amplitude is constant. Or it's being constant means that whoever is doing the oscillation may decide what to take as a maximum displacement. Okay, so amplitude is known, or yes, can be decided on, and then omega, angular velocity, can also be decided, or it's all not can be, it's constant, because a body executing simple harmonic motion does so at a constant angular velocity. So out of the equation, the only changing variable can be displacement, because A can be constant and omega is also constant. How about you? Okay.
Yes, yes. So, sir, they'll be given in the question.
Let's just solve this example. And that would answer you. An object attached to a spring. I hope you are writing.
Yes, please.
An object attached to a spring oscillates in the vertical plane. So vertical oscillation oscillates in a vertical plane without, vertical plane about a rest position O. About a rest position O. Hold on, I want to send a shot. Yes, Multity, your hand is up.
Please, can you please come again?
Oh, I'm even uploading the question on the platform. Okay. Okay, so I've just sent it to the platform. An object attached to a spring oscillates in the vertical plane about a rest position O with an angular velocity 4 radian per second and amplitude 10 centimeter. With an angular velocity 4 radian per second and amplitude 10 centimeter between extreme positions A and B. Yes, between extreme position A and B. So A and B are the extremes. Calculate I, the velocity when crossing the rest position. The rest position is the mean point. I. Calculate the velocity at the extreme ends A or B. And I, the velocity at a point 6 centimeter from O. Then IV, the maximum acceleration. Then I added another question in red pen or ink. Calculate the minimum acceleration. So I want you to try the first three. The velocity when crossing the rest position, the velocity at the extreme ends, A or B, and the velocity at a point 6 centimeter from O. I'm giving you 6 minutes to give that a try, and I'll come back to you. Start work. It's up. Let's go through it, and then as we discuss it, you mark yourselves, okay? So, an object attached to a spring oscillates in a vertical plane about a rest position O with an angular velocity 4 radian per second. So, Abba, hello, Abba.
Yes, sir.
The angular velocity is given
Yes, please.
because a body executing SHM has this. Then an amplitude 10 centimeter. A is also given. Okay.
Yes, sir.
Calculate the velocity when crossing the rest position. Calculate the velocity when crossing the rest position. Let me hear from you what you had for this question. What did you get for the velocity when crossing the rest position? Share your answers with me. Natalie.
40 meters per second, or if you use
40.
the positive, sorry, if you use T equals capital T over 2, you get 40 meters per second. But then if you use T, you get negative 40 meters per second.
Okay. Do we have any other answer? Any different answer?
No, please.
Okay. Amma,
Sir, please, I got 0.4 or negative 0.4.
so let's share answer 0.4 meter per second or negative, yes? there are extremes. So, okay. These are the two answers we have. Let's see. We have to calculate the velocity. Generally, we know that the velocity, okay, velocity of a body executing SHM in terms of displacement is omega times a squared minus y squared. Okay. Now, we were told that calculate the velocity when crossing the rest position. So we can solve this question using this or using the in terms of time. This is because at the rest position, if I'm to use displacement, excuse me, I want to change my markers. If I'm to use displacement, I know that at the mean point or rest position, y is equal to 0. So if y is equal to 0, then v would be equal to omega times a. Omega times a. Omega is giving us 4 radian per second. And this is in SI units. Once omega is in SI units, then the amplitude A must also be expressed in SI units. So times 10 to the power minus 2 meter. Okay, so Natalie, you must convert to SI unit because the angular velocity is given to you in SI unit, radian per second. Are you okay? And so we have 4 times 10 to the power negative 1. And obviously, because all variables are in SI units, V will be in meter per second. Therefore, 0.4 meter per second will be our final answer. If we want to use this, then at the mean point, t is 0. So if t is 0 or t would be equal to the period when it goes and then come back. So if you use t is 0, you have v is equal to a omega cos. When t is 0, this will be 0. So cos 0. Cos 0 is 1. Therefore, you have a omega as, and that will be equal to 0.1 times 4, which is 0.4 meter per second. Please, is everybody okay here?
Yes, sir.
All right. Question 2. The velocity at the extreme ends. Here, I mean, you can just quote your answer straight away. Priscilla, what did you get for velocity at the mean point? Sorry, at the extreme. What did you get for velocity at the extreme ends?
0.
Why 0, Priscilla?
You stay there because when we solve it, that's where we go.
Pardon?
Mr. Eager, please, you said when a body is undergoing a simple harmonic motion, its minimum velocity is at the extreme.
and that is 0. Straight away. Okay, so that is right. If you still want to show it, I'm coming. I want to drop attendance. If you still want to show that coming in. All right. If you want to show this, then at the extremes, the displacement y is equal to what? At the extreme, the displacement y is equal to. Oh, who is helping me? At the extreme, the displacement y is equal to. Hey, Lane. Hello. Samuela.
Yes, sir.
At the extremes, the displacement y is equal to. So what's the displacement at the extremes? Okay, Carl. Carl is not there. Yaba. Hey, people don't want to talk. Oh. Ama.
Yes, sir.
At the extremes, the displacement y is equal to.
Amplitude.
It's equal to the amplitude. So if y is equal to a, then the velocity at the extreme v would be equal to omega, which is 4 times a is 10. So 10 squared minus y, which is equal to a 10 squared. Straight away, whatever we have within the bracket is 0. And so velocity is 0. So this is another way of showing that at the extremes, the velocity is 0. If you want to use displacement. If you want to use velocity time, then it will take quarter of the period to reach the extreme, one extreme, and v will be 0. And it will also take 3/4 of the period to reach the other extreme, and v will still be 0. All right. Then the velocity at a point 6 centimeters from O, I. Velocity at a point 6 centimeters from O. Let me see what you had for this question. Amma, what did you get for this particular question? Natalie, what did you get?
8 meters per second.
So Natalie's answer is 8 meters per second. More views. Natalie, I just like your confidence. That's what I want. Share your views, no matter the situation. Lane, What did you get for this question?
Please, I
Hey,
went
Lynn,
off. Which question?
the I. The velocity at a point 6 centimeter from O. Did you get there?
Please, I had 32 meters per second.
32 meters per second. Then the last answer. Herbert. Herbert,
Yes, sir.
share your answer with us.
Sir, please add 18 meters per second.
15. Okay, so let's see. We have to find the velocity at a point 6 centimeter from O. So what are we given? We are given displacement to find V. So clearly, we can only use V connecting displacement to solve this. Here we can't use the time because what we have isn't about time. So V will be equal to omega is 4 radian per second, amplitude 10. But since this is in SI unit, we convert amplitude 0.1 squared minus, we convert the displacement to meter. 6 centimeter is equal to 0.06 meter. So figure this out for me. 0.1 squared minus 0.06. Yes, what's the answer? So what we have within the brackets is 0.0064. Oh, okay. 0.0064. 1, 2, 3. So when you take the square root of this answer, you have 0.08 times 4. The answer is 0.32 meter per second. So you see, your problem is that your problem has to do with conversion. Your problem has to do with conversion. Please, whenever you are giving different values and others are in SI units, others are also not in SI units, then you must quickly convert all other values that are not in SI unit to SI unit to work with. Else, there is that inconsistency in the values you are dealing with. Okay, sometimes you'll be given acceleration due to gravity. G is equal to 10 meter per second squared. And all other values are not in SI unit. Because you'll be using this, which is expressed in SI unit, all others must be converted to SI unit. Because if this is in centimeter per second squared, the value will be different from this. So that is what you need to, take note of. When others in SI unit and some other values are not, you must quickly convert those without in SI unit to SI unit to work with. Please, is that clear? Hello, are we okay?
Yes.
Yes, sir.
Yes.
Okay. All right. So the next thing I want us to look at is acceleration. We have about 22 minutes more to go. So let's quickly talk about acceleration because I want to finish SHM quickly. We've treated velocity, displacement. We've treated velocity in terms of time, in terms of displacement. Now, because the velocity is also a cosine function, it means it is also harmonic or a varying function. And yes, it is. The reason is that while the body oscillates, we realize that even with what we've just looked at, the velocity is maximum whenever it's crossing the mean point. It is 0 here, it is 0 here. So as the body oscillates up and down vertically, its velocity changes. Okay. Maximum here, when it's going up, it is increasing. By the time it gets to this extreme, it has increased to 0. When it is coming back, decreasing. By the time it gets here, when it is coming back, it is increasing. By the time it comes here, it is maximum. When it crosses the decreasing. By the time it gets to the other extreme, decrease to 0. So it is repetitive thing. Its velocity is always changing. And V is equal to A omega cos omega t for vertical oscillation. And because it's a sine function, we can plot it, equally plot this on a graph. Just as we did for displacement. So let's plot the velocity function with time for one cycle. So quarter of the period, half three quarters, and then t. We are only plotting it for one cycle because it's a repeating thing. The amplitude, the maximum velocity is this. So this is a graph of V against T. We have A omega as the maximum velocity. We have minus A omega as the other maximum velocity. And this is a cosine graph. Cosine graphs starts from the amplitude. So at time t is equal to 0, what will be the velocity? Look at it. When t is 0, we have cos 0. Cos 0 is 1. So velocity will be equal to the maximum value. So at t is equal to 0, this will be the value of the velocity. Maximum at the mean point. Now at t is equal to quarter of the period, what will be the velocity? Please calculate and then let me know what you have for the velocity. At time t is equal to quarter of the period, what is t? What is the velocity? We've done this, so please calculate and tell me what the velocity will be. Samuela, Len, Amma, Priscilla, Equiadoma, and the rest of you, I'm waiting for you. At t is equal to quarter of the period, what will be the velocity? Is anybody ready?
Sir, please 0.
So this is 0.
Or
At t is equal to half of the period, what is the velocity? At t is equal to half of the period. Hey, let's hurry up.
sir, please negative.
Of negative a omega.
Yes, please.
Yeah, so it's a sketch. So this is at t is equal to 3/4 of the period. T is equal to 3/4 of the period.
Sir, please 0.
So and t is equal to the period. At t is equal to t. Yes,
Sir,
at t is
please AW.
a omega and what kind
Sir,
of
please A W. Hey, sorry, A omega.
Sorry.
So we've plotted it. Now let's join the plotted points. So this is the velocity graph of a body executing simple harmonic motion for one cycle. Let me caption this. The velocity graph of a body executing simple harmonic motion for one cycle. If you have to draw it for 2 cycles, it's easy. Just, okay, 2 cycle, quarter plus this. On and on and on. So 2t. Then it will be a repetitive thing. It will be a repetitive thing, that's all. So when you understand it, if you have to draw it for whatever cycle, 10 cycles, what you can still do it. Class, is that understood? Is it understood?
Yes,
Yes,
please.
sir.
Okay. Acceleration. Acceleration of a body executing simple harmonic motion. Acceleration. Now look at why acceleration. This is an oscillating body whose velocity is always changing with time. When it is here, it has a maximum velocity. One is going up, decreasing, decreasing, decreasing. By the time it gets to one extreme, it has decreased to 0. When it is returning, increasing, 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 increasing. By the time it comes here, it is maximum. At the other extreme, it is decreasing, decreasing, decreasing. By the time it gets here, it has decreased to 0. Okay, so V is 0 here. V is also 0 here. V is maximum. So we see this body's velocity changing with time. And whenever there's a change in velocity with respect to time, we have acceleration. Okay, the reason for which we are considering the acceleration function of this body executing simple harmonic motion, because we see its velocity changing with time. Okay, and since acceleration A is equal to the rate of change of velocity with time, dv on dt, meaning that to get the acceleration function, we need to differentiate the velocity function with time. So A omega cos omega t. And don't forget that we are only looking at the body oscillating vertically, the reason for which we have this. Please, are you okay? Class, are you okay?
Yes, sir.
All right.
Yes, please.
Unfortunately, I must sign off here because I've been warned by my earpiece that the battery has gone down. So we've got into acceleration, meaning we are accelerating so well. Okay, we are accelerating so well. So we'll continue once again on Friday. But before then, I'll supply you with questions to try. Until then, please have a very good night and take very good care of yourselves. Bye-bye.
Thank
Bye.
Okay.